Hi, welcome back. So in this chemistry lesson, we're going to go a little bit further with electrons. We're going to specifically focus on energy levels and orbitals and exactly what those mean and what they look like and how they're related to the periodic table. Again, this will be fairly important going forward when we try to understand molecules and bonds and several other things. So here again is our periodic table. And it's broken into these chunks. They're called blocks. We have the S block, the D block, the P block, and the F block. Now what this means is any element located anywhere on the periodic table, if it's right here in the P block, the 2P block, its location tells you where its highest energy electron is. So we read a periodic table left to right, top to bottom. So we'll go 1, 2, 3, 4, 5, 6, 7. That's the seventh element. It's nitrogen in this case. In each of these orbitals, in each of these blanks, we can fit 2 electrons. So we get 1, 2, 3, 4, 5, 6, 7. That's where the final electron will be. It'll be in 2p3. 1, 2, 3. Right there. So we have some more examples of this that I'll demonstrate with you. So again, here's the hydrogen atom. So it's got just 1 electron. Its atomic number is also 1 proton. So there it goes. And then helium goes right there. We always fill the lowest possible energy level first. So that's where the 2 electrons end up. And this is the 1s orbital. And I'm going to show you the orbitals towards the end here. So then we jump to 2s. That would be the lithium atom. And then beryllium, I think, is the next one. So there we go. Then we jump to the P. So that's boron, carbon, and nitrogen. So what you'll notice here is the electrons are not pairing up. The electrons are jumping into separate orbitals each. Now the reason for that is because electrons are negatively charged. They repel each other. So they will not partner up until they have no choice. Now if we go backwards, as we jumped from lithium to beryllium, well, why didn't the electron just jump up here to this 2p spot so it could be alone? Because that's higher energy. It's literally higher up here on the periodic table. And the sequence, lowest to highest energy, as we go from bottom to top on here, is the same as it goes left to right. So notice that 2s1, 2s2 comes before 2p1, and that's because it's lower energy, and so it literally comes before it over here too. So anyways, it does not jump up there because that's too high of energy. Electrons are fine with pairing up if it means that they have to spend less energy. So they go solo here, and then we go on to oxygen. Now they have no choice but to pair up, and then the fluorine, and then the neon atom. There we go. Let's jump way ahead. I think this is manganese at that spot in the periodic table. It doesn't really matter. So here we're at the 3D. So we filled out all this other stuff. We did that P row, and then we went to the 3S. There we go. Next across is 3P. It's the next highest in energy. So we fill out all 6 of those, and then 4S. Now we're on the Ds. So they electrons single up first into their respective D orbitals. And then as we move across, I think we get iron, cobalt, nickel, copper, and zinc. I think I got the order right. So now they start to pair up once again. So that we can only fit 2 electrons in each of these little subgroups. I just call them orbitals. And the number of orbitals in each block is different. There are 3 orbitals in the P block. We can fit 2 in each of them, so there are 6 elements across. There are 5 orbitals that can each fit 10 inside of the D block here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the F block, there are 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that means there are 7 orbitals on there. 1, 2, 3, 4, 5, 6, 7, as we can see right there. I guess this does keep going again. So we get to the P block, and then, yeah, we're just filling in these spots one at a time. And then we can double them up. And then when we get to a noble gas, they're always noble gases are always filled in that p orbital. So here again are what the orbitals look like, but I have a much better way of explaining them in this video. So that's the s orbital. All s orbitals can just fit 2 electrons in total, and there's only one s orbital at each energy level. So notice that the s is just this column right here. So there's only one pair of electrons that can ever go there. Whereas in the d, there are, like I said, 5 different shapes, orbitals for it. But again, each one is at a different energy level, so they get farther away from the nucleus. So this gets really confusing when we start adding the p and d's in there. So I just have the s orbitals in here. So there's the 1s, the original one. Then here would be the 2s on the outside, so that would be like where lithium and beryllium are. And then where the sodium and, can't remember what comes after sodium, that would be the 1, 2, 3rd energy level, then the 4th and 5th. In total, there are 7 of them. But they just keep growing outwards from each other. Here are those p orbitals, and a total of 2 electrons will be found they exist in a superposition inside of there until you measure them, but those are the areas where they can be found. But again, these are overlapped too. Here are the d orbitals, so there are 5 different orbitals that can fit a total of 10 different electrons. And again, these overlap too, so it starts to get really crazy looking. And here are those 7 f orbitals, and I did not bother trying to overlap these. It would be too complicated. So if we reimagine these energy levels and put a picture of each of the orbitals in there, then it looks like this. And I think this is kind of, to me, this helps it make sense a little bit. So instead of counting electrons, we're just displaying one orbital. We're just displaying one orbital at each of these, we can call them sublevels. And you just have to remember that a maximum of 2 electrons can fit in there, a maximum of 2 electrons can fit in there, or in there, all the same. So if we just pick some random element, that would be the carbon atom. It's the 6th element, so we got 1, 2, 3, 4, 5, 6. That's where the electrons go. If we move to, I have no idea what that is. I think it might be molybdenum. I did this lesson with my students earlier. It gets all of these filled up. So these are where all of its electrons would be. All of them would be paired. You would find 2 electrons in every single one of these orbitals, except for the final ones, because we only got 1, 2, 3, 4. So those are going to have single electrons in them. We'd have to jump to this element right here before we would start doubling, and then that would be our only orbital with 2 electrons in it. So one other thing I want to show you is we have electron configuration where we literally spell out which electrons have been filled, which orbitals have been filled with how many electrons, and we do it in the sequence of energy. Now I won't be focusing on that this year because it's only important for the sole purpose of learning electron configuration. To me, it doesn't help enough with things we learn about in the future to waste time on it. So right here we have nitrogen. This is its final electron configuration. It has 3 electrons all filling up the 3 p orbitals. Now, elements that are in the same group as one another, they have the same chemical properties, and they get that, because of that, they share electron configuration. So if I jump to the element below it, directly below it, they have to be in the same group. It'll have a whole bunch of extra electrons, its atomic number and mass are much greater, but at its highest energy level, it has the same electron configuration. So we can see 1, 2, 3, 1, 2, 3 right there. So hopefully that helps make a little bit more sense of electrons and orbitals and energy levels. See you next time.